Hello, everyone. Welcome to the 11th episode of Math and Beyond on this podcast. Today, we start, let's say, sort of a collaboration with Shounak Bhattacharya. He is a teacher of mathematics and physics, and he's, let's say, a self-learner mainly for topics as General Relativity, topology, differential geometry, quantum mechanics, and related. So today we are going to start with the first episode of this, let's say, series of episodes that we will be doing together, and we will be talking. We will start talking about general relativity and Einstein field equation. So now we'll send him the invite, and I will see you shortly. Hi, Shounak. Hi, good morning. Good morning for me. Hi, Shounak.
Hi, how are you?
Hi, I'm doing fine. Good morning.
Good to see you. Yeah, good morning. Is this, if I fade out the background, is this okay, or shall I keep the background on?
No, absolutely. Okay? It's fine. It's totally fine.
Wait, just a second.
It's great. How are you doing today?
I am absolutely fine. Quite excited to participate in this podcast.
Yes.
So busy with various other things, making a very interesting video, which I told you, God does not play dice. So something like that, as well as something more videos which are coming up, and very excited. I saw a few of your, podcasts also. It is great. I mean to say, it's a wonderful job that you're really doing. So
thank you very much.
And this is something, because podcasts, I would say, around about 10, 12 years back was quite good. I mean to say, they were very popular. But as things started off, podcast didn't become so popular because people were more into videos, etc. So that is why, but now it is good that podcasts have started. Right. Okay. Just give me a second. I will just see one more thing. Is this background okay, or this background? Earlier one was good.
Really, there is no, I think it makes, to me, it's very much the same. You can keep this one if you want. I like it the same.
My bookshelf over here, so that's it, and a refrigerator. And this one, I think
it's no problem, Shounak. Don't worry.
I think this one would be okay.
People are here for the content.
Content, right? But still, look or something matters. So I just thought to. Okay, so shall we start off?
Yes, I think we can. I said before sending the invite, I gave a small introduction about you, and I said that.
Okay, what is the name? I would like to ask one thing. What is the name of your this channel or this episode? Then I can refer to that name.
Yes, the name of this episode will be General Relativity and Einstein.
I mean to say your name, your channel.
Okay. My name is Francesco Cavina, and the name of the channel
saying that the podcast that you are making. Do you have a kind of a program name or the name of your channel or anything like that?
Yeah, it's called Math and Beyond, and this podcast.
Math and Beyond.
Yes.
Okay. Just hold on. I will put on the headset.
Okay, can you hear me?
Absolutely. We can go ahead, right.
Great. Make a try.
Am I audible? Is this clear?
Yes, great.
Okay, yeah, we can start.
Okay. Do you have any chance to have the microphone a little bit closer? I don't know.
I can hold it like this. Yeah, we can do that.
If you want, because I think it was I'd say you can hear a bit let's say less louder. That is why. Okay, great.
This is fine. Yeah.
Okay, and so I think we can you can jump into it. I gave an introduction about you and about the episode. Today we are going to tackle general relativity and Einstein field equation. So we can dive into it, and I will ask you. 1915, we are in Einstein, let's say 10 years after Annus Memorabilis of Einstein, of Albert Einstein. He comes out with this basically geometric theory, which is a theory about the geometry of our universe. It revolutionizes literally our understanding of gravity, and it is the theory of general relativity. What is the meaning of this theory? What does it represent? What is GR, general relativity?
Yeah, because as I told you that in the next episode, I will make a presentation by sharing my screen where I can actually show you the mathematics of time dilation. And what you asked, coincidentally, I have worked upon, that is called Penrose's hypothesis of, generating power in case that the light bends around the outer horizon, that is the event horizon, so that we can do. But that, I would say, that would be better if you take up in the next episode, because that will take some time, a few slides to prepare, and that also goes a little bit time dilation to special relativity. So we keep those questions something very specific to general relativity, and in the next episode we can take on. Yeah, good time to start. Yeah.
Okay, so what is general relativity? What is the meaning of this theory? What is this theory about?
Okay, so first of all, I would like to thank you, Francisco, for inviting me to this very special podcast. I've been watching this and you are doing indeed a great job bringing a lot of astronauts, men of mathematics and science across it. So I would like to tell a little bit about myself, not much. My name is Shounak, and I'm a very, very passionate science enthusiast. And what I really try to do is to spread the light of science and mathematics in a very easy manner, trying to make easy videos and explanation to the most complex mathematical or physical understanding, especially relativity, differential geometry, topology, and so on. So to first answer your question, Francisco, that what is general theory of relativity? Well, I would like to say that there is a kind of a notion in answering this question. First of all, we call it general theory of relativity. We generally know that it is a theory of relativity which relates to the space-time curvature and defines gravity not as a fictitious force, but something related to the space-time curvature. Now, this is the general thing that we all know. I mean to say we all talk about that. But there is one very subtle thing which we do not observe. First of all, we call it general theory of relativity. Now, see why we call it relativity, because it all started with Einstein's mass energy equivalence when he found out special theory of relativity, which specifically takes place only in inertial frame of reference, not in the accelerated or non-inertial frame of reference. Now, I was talking to one of the scientists in Russia, and he told me that, Shounak, see, general theory of relativity cannot be called as a theory of relativity. I questioned why. So he gave me a wonderful answer, which I still remember. The theory of relativity actually ends in special theory of relativity. Because the relativistic effects, which one is relative to each other, the frames of reference, that all ends at special theory of relativity. In general theory of relativity, we only talk about the geometry of space-time, the space-time curvature, more on the manifolds, differential geometry, etc. So what we can talk it in a sense that it is a general theory of geometry. I mean to say, if we can recoin this term as general theory of geometry. So yes, it is basically our a new understanding which was proved in 1915 by Arthur Eddington on the solar eclipse which happened on 29th of May, which is coming in a few days from now. And that was the time when the world came to know that yes, the space-time's presence causes gravity or the light to bend. Although we remember that it was already framed in the books of mathematics in 1915, but as we all know that mathematical theories require a hardcore experimental evidence to do that, and that was done 4 years later. Let us also remember, Francisco, that during that time, even Albert Einstein faced a huge amount of criticism. so did Galileo, so did Newton, and everything. And nobody was actually willing to show off this age-old concept that gravity is a force. So just to answer all in one, that yes, it is a theory of space-time geometry, which gave us a complete new understanding of space-time, where the concept of gravity as a fictitious force, a force which is responsible for things to fall and the planet and other celestial matters to move around, has been, I won't say abolished, again, that would be a wrong term, has been extended by Einstein into a better theory, which is called general relativity.
Okay. What does, you mentioned that we have gravity not as a fictitious force anymore, but as a consequence of space-time curvature. And may I ask you, what does cause space-time curvature? Like, okay, why does space-time curve? Like, just because it wants, just because it is an even day? Or what does space-time?
Yeah. Thank you for this question. You know, I was discussing to one of the astrophysicists I found in LinkedIn, and he also told me that, Shounak, let us understand, we all know how it happens, but we really don't know why it happens. And you know, the entire problem of physics spins down when you say why light travels in a straight line. I remember the physicist telling that because it wishes to be so. That is the fundamental, you know. Now, why light bends when it, or the velocity of light loses when it enters a denser medium, because it wants to be so. So we all know how. And, you know, I remember my mathematics teacher telling that when we ask why, they tell, shut up and calculate. So the basic fundamental, you see, the entire search of physics through eternity has been to find out the ultimate answer, why. And to be very honest with you, though I'm a man from mathematics and science, I will still say that the search is going on and we really have not found out why, but we are more into how. But anyway, that is a philosophical question. Okay, so answering to you what causes the space-time curvature, I would like to take you as well as the viewers who are watching this video a little bit back, because until we understand the background, it would be difficult for us to understand what is the space-time curvature and why it happens. Now, as you see that there is a famous story, if you don't mind, Francisco, allow me just 2 minutes to tell about that. And this is about when Galileo framed that the Earth moves around, the heliocentric concept of physics. The Pope took him under house arrest during that time, as you understand, and he was bound to walk under the house arrest. Now, when he was taken to the church and he was, you know, forced to tell that this is, you know, I would say blasphemy, and you have to admit whatever you have told is wrong. And, you know, I remember Stephen Hawking's that book, Galileo told that, okay, I admit what it is wrong. Maybe my pronunciation is horrific for Italian words, but he said something called "eppure si muove." I don't know, you will be the right person to say.
Eppure si muove.
Okay, so that's it. Eppure si muove. But still it moves. So you see that what it actually started from there, the revolution of science, that whatever you do to a person of mathematics of science, I would say the truth will always remain. Now, when Galileo founded that observation of Earth moving around the sun, it was then Isaac Newton, who during, as we call it, the COVID times. So what did, Francisco, during COVID times? Really nothing productive, right? We stayed at home. But similar kind of a COVID happened during that time in 1600 in Cambridge, in England, when Isaac Newton was staying nearby and he was attending Cambridge School. And during that time, a pandemic broke out. Now, see, I always tell my students that let us be very productive. So Isaac Newton took that advantage of COVID or the pandemic and stayed at home for 2 years and revolutionized physics by inventing gravity and whatnot. We know that. So you see that even that time COVID happened, and ours also COVID happened. So see you, the genius of Isaac Newton. So he basically framed the laws of physics. We never know that actually whether an apple fell on him or a guava fell on him, but whatever be it, but he discovered gravity and he framed it on Philosophiae Naturalis Principia Mathematica. I would like to draw an attention, which most of the viewers might not be knowing. Isaac Newton was very skeptic in order to publish his Principia Mathematica. Why? Because he thought that he would meet the same fate as Galileo. And it was during that time a very close friend of his, Edmund Halley, actually came and told me, what the hell are you doing? He told her, no, I'm not going to publish because otherwise I might face a problem. So you give me those notes. That is the Principia Mathematica. And Edmund Halley, out of his own pocket, went down and published those notes, which changed the entire scenario of mathematics and physics. So just to take you in a nutshell, is that this was the invention of gravity as a force. And if you read Principia Mathematica, you will still understand that Newton was also not sure about this action at a distance. We call gravity action at a distance because no two forces touch each other, but yet they are attracting each other. So he was also not sure. Now, after that, what happened with the special theory of relativity and Einstein arriving at our physical arena? So he thought that, for example, let me give you an example. I'm sitting on a chair, right? I'm talking to you. And this was done in the Swiss office at Bern. And I remembered that line where Einstein is telling that cloistered place on earth where I hatched the most beautiful feelings. That cloistered place on earth where I hatched the most beautiful thoughts. That means if you go to Swiss office in Bern, you will see it is a very small place, just a desk, right, and a chair with lots of people coming around, talking, shouting about patents, etc. During that time, the golden moment struck. And what was that golden moment? Einstein thought that if I'm sitting on a chair and a table, what would happen if the floor collapses? Now, this is kind of a bizarre, weird feeling. Why will somebody think that the floor collapses, right? God forbid it should not happen to anybody. Now, if the floor collapses, he starts falling. And he thought that, well, I am falling in the free space, that fall, and if I'm on an elevator, which I'm falling, or which is accelerating downwards or even upwards, I won't feel any inertial, any kind of a force. Also, he did a kind of what we call a Gedanken, 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 or the thought experiment. Again, sorry for my terrible German pronunciation, but it is something which is called a thought experiment. Which he thought that if the elevator is accelerating up, and if you shine a light, then the light ray won't go straight. As it accelerates up, it will bend down and down and down. Now, why is it that it is bending down? From there, he understood that means there is something which is called a curvature. Now, if I'm falling down, or if I'm standing on earth, right, the heavy weight that I feel on my shoes, and every day, Francisco, to be very honest with you, every day I feel that when I'm moving on the 14th floor of my college, and when I'm standing on the elevator, I just think of Einstein, and I thought that he did this kind of an experiment, because that is something which I can really feel standing right here or sitting right here, and the floor which is causing a thrust, there is actually no difference. That means, given that kind of a situation, there is no difference between the acceleration and the gravity, that feeling that we have. So to answer your question and cut things short from history to the present, that actually that was the culmination point when Einstein thought that, okay, that means we cannot call gravity as a force. Now, remember, there is also one thing important to understand. Can we see a force? No, we don't. When the wind is blowing, we see the effect of wind on the trees. And there is an repulsion or attraction of electric forces, we see the effect of electric forces on the electric charges. But can we see the force? No. So the question is that there is no chance of seeing gravity, only feeling that force. So that actually made Einstein feel that that means there is no force, because if I'm standing on an elevator, getting the same kind of a feeling, and standing on the floor, getting the same kind of a feeling, then how can you call it these two feelings are different? Then where is gravity? That was the basic, I would say, a golden question asked on his own mind. And the thought experiment that he did with the elevator, where he showed that the light rays actually bend. And that actually proved, I mean, it was not proved, but hypothesized to Einstein that there is something which is called a space-time curvature, and that is responsible for all those things which are happening around.
Okay, so this space-time curvature, Einstein, in General Theory of Relativity, clarified that it is caused by objects with mass. So any objects around itself causes space-time to curve. And one may be wondering, okay, whether I don't see the places around me curved by my presence, because you're not a massive object. We are relying on this, we are, let's say, traveling and I will now introduce the term that I will ask you about in a minute. We are sort of traveling the geodesics of space-time, as well as doing the Earth, traveling the geodesic of space-time around the sun, as the sun and our solar system is traveling the geodesic of space-time around the center of our galaxy. And basically, what is I now said this term, which looks fancy, but what is a geodesic? What is a geodesic? So why does it relate to space-time, and why it is actually is a very when I first read about special relativity and general relativity, I encountered this term very, very frequently, and I tried to wrap my head around it. But why is it so present? Why is it so relevant in this theory?
I will tell you. Yeah, excellent question. It actually shows the intriguing science mind that you have. First of all, let me tell you that it might be an obvious question that you just told that there are things around you, right? And we know that general theory of relativity measures the space-time curvature. Now, the viewers as well as you might have a question that this table, this chair, this apple, this pillow cover, this sofa, they also exert a force on the earth, right? The question is that, can we measure those trivial things with the space-time curvature, with the Einstein field equation? That is very important. That if we can measure the curvature, then why don't we use Einstein field equation to measure the curvature of my body or that thing? So now here is something which I actually showed in my last video, that practical application of general relativity. Now you see, we will come to the Einstein field equations later as we go ahead with the episode. The thing is that if we take the densest metal on Earth, that is called osmium, which is around 10 to the power 22 some cubic measurement, and if we accelerate it at the speed of light, that is c squared, we multiply it by c, the densest material, understand, but still we get a rest mass of that material, which is 10 to the power minus 22 something. If you watch my video, I have the exact number, I don't remember. That means what? Now, if you remember, before answering to geodesics, we need to understand that there is something which is called a Schwarzschild radius, which if you squeeze an object, then if it turns down to that critical radius, it turns into a black hole, right? Now, the thing is that all these things which we see around your room and my room, this cupboard and everything, can be turned into a black hole if you can squeeze that to that critical radius. The problem of measurement is that we cannot use Einstein field equation to something very small. Now, question is that what is very small? I would say even the Earth is very small. Even 10 Earth is very small. So that is why we have to take beyond the terrestrial objects and have to land something in Jupiter, Sun, black holes, supermassive black holes, etc. What I'm trying to give the viewers an understanding is that general theory of relativity's equations are not applicable to our life, because even if we take the densest material and try to accelerate, we get such a negligible amount of curvature that the field equation would fail to answer. So that answers the question that it is only applicable to very, very, very massive objects, which we cannot find on Earth, number one.
Number two, coming to geodesics, which you rightly told. Now, I would like to give a kind of an information that, remember, geodesic is nothing specific to general theory of relativity. It's a wrong notion, which I see most of the students have. Geodesics has been studied even by Bernhard Riemann since 1895 in differential geometry. So differential geometry actually deals with geodesics, curvatures, Lemaican curves, and a lot of complicated mathematics. It just tells the shortest path that a straight line takes. That's it. The shortest path that a straight line takes. Now, if I get 2 points on a Euclidean or a Cartesian plane, it would be a straight line, simple. Now, if you take a curved surface like I have on my hand, then what will happen? That the line will bend. Now, this line bending is basically due to the presence of mass on that surface, which causes a dent, which causes the curvature to bend down, either positive or negative curvature. That is a different issue. But as you asked me that what is geodesics and how it is related to general relativity, we should remember that it is nothing to relate with general relativity. It was already there in differential geometry. And to tell you one more thing, most of the viewers might not know, I was reading a wonderful book I would like to share with you, Francisco. The name of the book is Subtle is the Lord. This is written by Abraham Pace, and it's one of the best books of Einstein's lives and works. Subtle is the Lord.
Subtle is the large.
Lord, S-U-B-T-L-E, subtle is the Lord, right. So it says that subtle is the Lord, but malicious he is not. I am making another video on those philosophical implications. Now, subtle is the Lord actually tells that Einstein was not aware about differential geometry, about tensor calculus. I've shown numerous times in my videos. Now, when he was stuck up with this problem, I'm coming to geodesics, which is related to that. He went to Marcel Grossmann, one of his closest friend at Zurich Polytechnic, and he told, oh, Grossmann, save me, otherwise I will get mad. What was happening is that covariant theory of mathematics was impossible for him without the knowledge of differential geometry. And I am happy to inform you that 2 or 3 leading Italian physicists, Michel Besso, one of his friends, Tullio Levi-Civita, Gregorio Ricci Curbastro. So Levi-Civita and Curbastro made a seminal contribution in Einstein's general theory of relativity. Remember, I'm not undermining, hope the viewers do not take me wrong. Einstein was not aware about tensor calculus. We should know that, right? And then Grossmann told that, why don't you look at the works of Gregorio Ricci Curbastro? I saw that, photograph of Curbastro's house when I was making a video on tensor calculus, and Tullio Levi-Civita. Without those 2 people, tensor calculus or general theory of relativity would not have been possible. I'm being very candid and open with you. So it was that time when geodesics has been studied in Göttingen by Riemann, and he has already mentioned geodesics in his doctoral thesis at University of Göttingen, and there he coined the term manifold, M-A-N-I-F-O-L-D. So you see that 2 countries, 2 eras now joining each other to frame the general theory of relativity. So Tullio Levi-Civita's work on geodesics, followed by Gregorio Ricci Curbastro, followed earlier by the granddaddy of mathematics. I called him the granddaddy of mathematics, that is Bernhard Riemann. All contributed together, and it was Marcel Grossmann and his friend Michel Besso told that, hey guy, come on, Einstein, sit by my side. I'm going to teach you tensor calculus, something like that. But the fact is that geodesics were present. Now we know, this is again what I was telling you over telephone yesterday, we know that only geodesics mean general relativity. Absolutely not. This is a misnomer. This is a misconception. So geodesics are basically where these 2 lines would travel, right? Now we have got now the space-time curvature, and we know something which is called a stress tensor. That means if this mobile is right on my hand, it is creating a stress, right? It is a matter. It is creating a stress, and it is creating a curvature. And in this curvature, there are 2 lines which are moving, right? And what is the path of that line? That is the geodesic. Allow me to give you one practical example with me and one of my very reputed professor in India, Professor Amol Chaudhary, on whose equations Penrose and Hawking developed what is called Ray-Chaudhary equation. You can Google it in your computer now, which is called Ray-Chaudhary equation. Now, when we went to Amal Kumar Ray Chaudhary, he was sitting there, and I exactly asked you what you asked me. Sir, what is a geodesic? So incidentally, there was a tram which was standing on the road, right? And he told me that, okay, you tell me how would the tram travel or where would the tram go? So I told that certain conditions are given, position, momentum, and velocity. And if it is a second order differential, then we can definitely calculate what is the path and which path it will go. And Professor, you know what he told me, I still remember. He told me, ask a rickshaw puller, a person who pulls a tram, what will they answer? So I was thinking, oh, come on, we are talking of high-level physics, geodesics and relativity. How come it comes to a tram driver or a rickshaw puller? And he told me exactly, if you ask a rickshaw puller, the rickshaw puller will say, the tram will travel on the path which is right in front of that. And that is the concept of geodesic, nothing it, very simple. I still remember, professors, that analogy. That means that if the tram line is curved, the tram will go in the curved path. If the tram line is straight, because of the Euclidean space, it will move in the straight line. So that is basically how geodesics are related to relativity. If we lay out a curvature or a manifold which is curved, it is up to the particle which line it will follow. It might be straight or it might be curved. Now, because we are dealing with general theory of relativity and because it relates to space-time curvature, not straight lines, we try to interpret geodesics in a different way. But geodesics as itself, it is just a mathematical concept, and we do a lot of mathematics in differential geometry. So that answers your question that geodesics are actually which causes or the line that it travels or the line that it takes due to the curvature of space-time. And why is the curvature? Because of the presence of mass, and that is why we get a kind of a curved space path.
Okay, very, very clear. I also read many times when reading about special relativity and general relativity. I've also encountered many times the concept of a geodesics in let's say applied let's say to our Earth, meaning which I found is a concept. It's let's say self-explanatory, very clear actually, and it was the fact that for example, if you are on Earth, if you see it locally, so here where we lie, looks flat, right? Yeah.
Right.
Then there are also other people who says that the Earth globally is flat, but that is topic of another story.
Absolutely.
Okay,
yeah.
So Earth is round, and we see that to go from one end, let's say from the equator to the North Pole, if we look at it globally, okay, we have the Earth looking at the Earth from outside, from a far point. From the outside, we see that the straightest line that we need to travel to go from the equator to the North Pole is not a straight line. Okay,
absolutely.
It's not like a straight line that you would trace upon the Earth. Okay, it would have a curved path. Why? Because we are on a curved object, and that basically I understood. Okay, so on curved objects, straight lines are curved. Yes, and that's pretty much how how I depicted it immediately with regards to space-time and geodesics, meaning space-time curves. Then the geodesics of space-time will not be Euclidean straight lines anymore.
Right.
They will start bending and being curved surfaces. Curved lines.
Yeah, when we are moving in this fashion, when the geodesics are meeting at a point, we call it a positive curvature. When it diverges, we call it as a negative curvature. And if they move parallel, never meeting with each other, we call it zero curvature.
Yeah, which is I would say, which is very a topic of discussion with regards to the universe today, because I like to read about cosmology, and so a very open problem is whether the curvature, the geometry of space-time is either open, closed, or flat. And what you just said is, if you have positive curvature, then space-time would be, let's say, sort of a closed ball, meaning that space-time would be curved on itself. Okay, so we would have a closed universe with positive curvature. If we have negative, and indeed in this case, as you said, geodesics would meet, meaning starting from two different points in space-time, if I would be traveling the straightest line that I can find in space-time, I would be meeting with the other guy starting from another side of the universe, traveling his geodesic of space-time. If we had a flat universe with constant K0,
we will move parallel to each other.
The universe in this case, this is actually quite scary as a scenario, because I wouldn't, how do you say, I wouldn't really understand let's say, the overall geometry, or I would say the overall picture of the universe, because a closed universe is sort of easy to depict. But a flat universe, what do you say? Is it bounded, unbounded? Is it infinite in size, or is it infinite in size but unbounded? That's many questions that I have been reading about. And then we have lastly negative curvature, which is a hyperbolic. It would be a hyperbolic plane. Okay, and that is, I think, a very exciting topic to discuss about, which we may in the future episode have a discussion about. Sure. The thing that let's say saddens me is that practical observation from these days strongly emphasizes that the universe should be flat, which I mean, bad luck, but we should trust the observation, I guess. So okay. So that was it with regards to geodesics, and you mentioned a lot of tensors. You mentioned that Einstein, let's say, got introduced to some high-level mathematics, which I find beautiful, because sometimes this is a thing that also applied to Paul Dirac. I've heard I read this thing about Paul Dirac, that sometimes he said, when I couldn't be able to wrap my head around a theoretical concept, when I would not be able to see the way ahead of me, I would just follow the math and be led by it. And that's I think beautiful, and it reaches the understanding in the article published by Eugene Wigner called The Unreasonable Effectiveness of Mathematics, which explains a lot of this concept. But you mentioned tensors and differential geometry. Can we start tackling practically Einstein field equation? What is this? What is this term, Einstein field equation? It is just the equation governing the curvature of space-time, the geometry of our space-time. How does it work? Which now, if you allow me very quickly, I would like to go and show an image of the Einstein field equation, so that we can show let's say, I will share my screen. So can you see?
Right, absolutely.
Yes.
It's fine. I mean to say, I can explain that. Okay, so before going ahead for this this field equations, I would request you that this is a wonderful question. Let this equation be there. Now, what I would like to first tell you and the viewers also, see, it was 1905 when Special Theory of Relativity was published, and it is 1915 when General Theory of Relativity is published. So what is the span? The span is 10 long years. So we need to understand, me and Francisco, and to the viewers who are watching, that we are trying to do something very difficult. That means we are trying to coincide or summarize a 10-year-long mathematical journey into 2 episodes of podcast. I mean to say, you understand that how much of genius people actually participate for 10 years in developing what you see right on the screen. Okay, first of all, I would like to tell you again a misnomer that it is Einstein field equations, not equation. Why it is so? This is a plural, obviously that means. Now, I cannot show right now because I have to go back to my original videos, what the viewers and what we are seeing right now, which Francisco has wonderfully explained that what is field equation. Thanks for this wonderful question. What we are looking at is that there are 16 partial nonlinear differential equations framed in one single equation. And that is why we called it equations, not equation. So what you are seeing right now, the left-hand side and the right-hand side, these are a collection of 16 partial nonlinear differential equations, which took Einstein and several brilliant mathematicians to frame for 10 long years, which I would try to make my humble effort to explain it. So first is that, the first is that 6 of those equations are common. Now, when I say common, let me give a very non-mathematical example. What do we mean by common? So, for example, AB and BA are common. So, I mean to say 1 multiplied by 2 will give whatever 2 is multiplied by 1. So, that is one common thing. Then I can say that C multiplied by D is equals to D multiplied by C. That means what I'm talking of, basically the notions of associativity, commutativity, or the general laws of analysis or number theory. But this is just an analogy. My kind apologies. This is not the right way to explain, but I cannot go back to the matrices right now. Then I would have shown that 6 indices of the metric tensors are identical. But anyway, just to make people understand that these are certain things which are common. So if 1 into 2 equals to 2 into 1, it is common. 3 multiplied by 2 equals 2 multiplied by 3, common. So there are 6 types of common things, which actually has been negated by the mathematicians. And what we are seeing right now is a set of 10 partial nonlinear differential equations. Okay. So we have understood that. And we have also understood in this podcast that it was Einstein, Michel Bessot, Grossman, Levi-Civita, Gregorio Curbastro, and the granddaddy Bernhard Riemann. I mean to say the contribution was immense. All of them contributed to develop this equation, including David Hilbert. Okay, and many others. We will make into a general theory of history of general relativity later. Okay, so first we will go with the left-hand side of the equation. I will come to the indices later, but first I would like to explain as a whole what this equation all about. If you take the entire left-hand side of the equation, that is R mu nu followed by minus half followed by R g mu nu, it actually measures the space-time curvature. That means given a ball, for example, a very idiotic example, sorry for that, Francisco, but anyway, given a ball on a piece of mesh, how much curvature this ball would cause is being measured by the left-hand side of the equation, right? Then we get an equal to, because all the equations have to be equated with something. And then what we get is the right-hand side equation, that is the stress, energy, momentum, and other things I will explain soon. So that means that if I get a ball and I put it on my hand, that says that how much of stress it causes on my hand. That is measured by the right-hand side of the equation. So if I know how much amount of stress is being covered or strain is being covered, I know what amount of curvature is being measured. And that curvature is measured on the left-hand side. So I remember John Wheeler quoting this line, matter tells space-time how to curve and space-time tells matter how to move. That is a famous line which tells that matter obviously will tell how much stress, that means how much the space-time is curved, and space-time curvature will tell how much matter is moved, and both of them are equal. So that means this would be equal to this. That is a very, very, very layman and a very generic, I would say in my terms, it would be a wrong conception, but just to tell you to the audience that this is what the field equation is all about. Now, I would come one by one to those indices, and I will explain it as simple as possible. Okay, first I would tell you that there are certain indices which the viewers and we all know. What are those? For example, we already know 1 by 2, that is half, right? We know that. Let us not worry about that. We already know what is a capital lambda, right? I will come to what it is, but we already know. So let us not be worried about this. We all know what is 8, that is a scalar quantity, a kind of a number. And we all know what is a pi, 22/7, and we got wonderful films on the life of pi and other things. So we are not worried about that, right? We also know the good old gravitational constant by Sir Isaac Newton, that is g. And we already know c to the power 4, that is the speed of light. Now hold on, how can the speed of light be to the power 4? I will come to that riddle. That is really bizarre. But let us hold on that this is c to the power 4.
It's a very big term.
Yeah, absolutely. Absolutely. You're very right. I was skipping a kind of a suspense for all of us, right? So we got the half, we know lambda, we know 8 pi, we know g, and we know c4. So we already know this thing. So let us not be worried about making people understand. It is nothing very difficult or out of the world. Okay. I will come to the first left-hand side term, which is called R. And this is called the Ricci curvature tensor. Okay, I would come to tensor part later because I need to explain why tensors, why do we need tensors, etc. But for the time being, let us assume that tensors are nice mathematical objects which wear nice dresses, beautiful t-shirts, which Francisco is wearing right now, is looking great. So let us understand tensors are like that. Beautiful objects, mathematical objects, wear t-shirts, nice dresses, that's it. So that is the R part, which is called the Ricci curvature tensor. Okay, what is mu nu? The first hand indices is mu and the next one is nu. Now, these are indices which measures space and time. So there are 4 indices. We know that Einstein unified space-time into space-time. Now, don't ask me why it is. Again, it will take 15 minutes to talk. But as I told you, we are trying to sum up 10 years of thought into one equation. So he summarized space and time, something not different, something a nice, beautiful piece of apple where the space and time is encoded. So let us understand that mu and nu speaks of 0, that is the first dimension, 1, that is the length, 2, that is the breadth, 3, that is the height, and 0, be it the time. So we get 4 indices, right? So now you see each of these mu nu, R mu nu is 4, G mu nu is 4, T mu nu is 4, right? And another G mu nu is 4. So we get 4 plus 4 plus 4 plus 4. How many? 16 indices. Now you see, I just talked right few minutes ago that out of 16 indices, 6 of them gets cancelled out, and we are looking at 10 nonlinear partial differential equations. These are the 16 indices. I hope I can make people understand. These are 4 plus 4 plus 4, 16 indices, and out of the 6 are common, we get 10 indices, right? Okay, now the question is that what does this Ricci curvature tensor actually does? In a very simple language, again, very sorry to those who are very mathematical bent, might find my explanation very bizarre. I'm sorry for that. It measures how much a ball deviates from a Euclidean space. Okay, let me make it further simple. We can tell it that it actually measures that if I move a ball in a flat space-time, right, it moves and moves and moves up to the end point. Now, if I get a kind of what Francisco was just telling, a closed universe, or when we are starting to walk from equator, we get into a kind of a close, right? So the ball, if you see, moves in a closed curvature, it shrinks in size. So the ball is there and it further shortens, shortens, shortens until it goes to the North Pole, right? And if you get a diverging geodesic, it will increase in size. That is an analogy. But what it measures, say, for example, that whatever happens in a Euclidean flat space, it measures how much it deviates from the Euclidean space to the space-time curvature of relativity. That is what R mu nu measures. Again, I repeat, whatever things are happening in a flat space-time, how much percentage or how much amount that movement will deviate from the flat space-time, that is what R mu nu measures. Okay. Now, what is this R G mu nu? after this half, that is called a Ricci scalar. Now, you have to excuse me, Francisco. Ricci scalar is something which is very, I won't say difficult, but it is challenging to explain, because I have to, before that, I have to make people understand what is called a Riemann curvature tensor, because Ricci scalar is a shortened form of Riemann curvature tensor. Okay, now I will definitely like to explain, because Richard Feynman told that if you cannot explain something to a 3-year-old, that means you don't understand physics. So right. Riemann curvature tensor, for example, to make things very simple, there is a kind of a curvature which is called Riemann curvature or Riemann curvature tensor, right? This is something I would later explain in the next part. It is a little bit technical. Then I have to go to covariant derivatives and then what is called parallel transport, all those things. So it is a kind of a curvature which is different, a little bit different Riemann curvature tensor. And that is, there is another great person wearing that beautiful shirt and pant and a bow and a tie, and that is a curvature, that is a tensor. And this tensor measures actually how much of Riemann's manifold differs. That's it. Now I would come to G mu nu, which is the central part of Einstein's field equations. Okay. Okay, let us give this kind of an analogy. G mu nu is the metric tensor. Now, what do we mean by metric tensor? Let me give a very simple example that what Feynman told, that we need to explain something clearly to a 3-year-old child. Now, what is the meaning of the word metric? It means measurement. So we have got kilogram, that is a metric, right? We have got a pound, that is a metric. We have got cents, that is a metric. We have got dollar, which is a metric, right? These are all metrics, right? What does it measure? Currency, weight, anything, right? Now, the problem is that in physics, we cannot use currency or dollars to measure. So what do? Is that we write something which measures how much things happen. Okay. Now, what is how much things happen? I will make you understand. Say, for example, I am right now here and I'm going to my college, and it takes around 1 hour time by a cab to move. So I can say that the metric from my home to my college is 1 hour. So we call it G office. Okay, G college. So that means the metric is what? 1 hour to travel from my home to my college. Now, suddenly I take another way round where I have to go via a traffic or some buildings, and it takes 1 hour 20 minutes to reach the same college. So what is the metric? Then I would say the metric is G underscore pond or G underscore traffic. That means that when I am measuring something, either in terms of currency or distance, etc., there is a kind of a measurement technique, which we call it as metric. Now, what is the distance between 2 points? We all know that it would be using the Pythagoras theorem, hypotenuse squared equal to base per perpendicular squared. So if I now take 3 points, it will be square root of x1 squared plus x2 squared plus x3 squared, right? Now, what is this? This is also a metric. What is the metric? Measuring distance between points. The question is that, Francisco, where does this metric work? It works on Euclidean space. It works on Cartesian space where things are flat. Now you see, we all do mathematics up till class 10, 11, 12 using this metric of Euclid or the metric of Euclidean space. Question or the problem comes that this measurement of hypotenuse squared equal to base squared plus perpendicular squared doesn't really takes effective place in the curved space-time. So what will we do? Now, if I go to Italy today, maybe Francisco might invite me someday or other. I might use US dollar or something, but that is a metric which really takes place on Italy or any place on this earth, any country. But if I move to Alpha Centauri and they tell that the metric for getting 1 glass of milk is GG, Tata, Roro, something odd, right? So that is the metric of Alpha Centauri's people who would ask me, change your currency of Italy or India or Germany to my currency so that you get a glass of milk. That measurement is what this metric tensor does. Francisco, am I been able to clear up things? We're taking simple examples. I think that's fine, right?
Yeah.
Okay. So the thing is that what is the metric that would take for me to convert the US dollar to the currency of Alpha Centauri? That is what G mu nu does. If you're really wondering, but this is my favorite subject. I can talk almost a day about metric tensor. Don't worry, I won't do that. But I have a very detailed 1-hour video on metric tensor derivation and other things in physics for students. You can later look up. Anyway, so G mu nu actually tells that, for example, you're standing on a field, okay, curved field, right? And some places the grasses are too dense. And some places the grasses are not dense, but they're spread out. The question is that how will I measure which portion is dense and which portion is less denser? That is what G mu nu does. And let us remember that G mu nu is the metric tensor, which is a central point. That means where the curvature goes down more. If I throw a ball, it would rush down. That is, means the gradient is high. And where the curvature is little bit, if I throw a ball, it would just flow down. That means the density of the curvature in one way, very technically, can be measured through G mu nu. So to make very simple things, it is the causal structure of space-time. I take the currency from US and go to Alpha Centauri, and I need to exchange it so that I can get a glass of milk or get what is desired over at a different planet. This exchange is being done by metric tensor.
Okay. Can I ask you to see if I understood correctly? So G mu nu. Let's say I now out of nowhere spawn a planet, a huge massive object, which bends space-time around me and around this object, this massive object. Through G mu nu, I can understand there how much space-time is curved, there how much space-time is curved. I can understand, let's say, mathematically the curvature.
No, you won't be able to understand the curvature. In order to understand the curvature, the full equations need to have a solution. Yes, you are very right telling that if you've got a massive ball, then you can understand the density.
Okay.
The amount of density that that ball has made through a surface, okay, where it is more, where it is less. I mean, it's quite complicated, I understand. But this is more or less. Now, you see, there is nothing called a layman's understanding. Either it is mathematical or it is nothing. So yes, the analogy that you have taken is absolutely right. Massive objects, how much dense it is in a particular area, that is what metric tensor actually does. Okay.
Okay, so wait a second. Because density, right, is mass divided by volume.
Yeah, but that is classical physics. Here it won't apply.
Okay.
The mass is not a mass. Then we have to take the relativistic mass, because mass won't be a constant mass, because if you're coming from special theory of relativity, it would relativistic mass. And what you told the equation, density is equal to mass. And if you take the momentum even, right, then it would be a 4-vector momentum, because let us understand, we are not dealing with 3-dimension, we are dealing with 4-dimension. So the momentum is called a 4-vector momentum. So that is why I was telling, all this needs to be plugged inside this equation to get what you are telling, that how much dense or how much curvature that huge mass is making at your home.
Okay.
Because everything changes. We cannot call momentum a momentum. We cannot call force a force. We cannot call velocity a velocity. All of them has been already plugged in special theory of relativity, 1905, using the 4 vectors. Now we are further generalizing from 4 vectors, which was there in inertial frame of reference. We are making it into arbitrary frame of reference, anything which happens into accelerated frame of reference. Okay. Don't worry, this picture will be much clearer as we move ahead, because I understand, as I told you, this is extremely complicated but I'm trying to make the best, easiest analogy. Okay, so we understood G mu nu, and we got a lambda, which is called the cosmological constant, which I would request again, Francisco, to read a book that is called Brilliant Blunders, as well as to the viewers. Brilliant Blunders, B-L-U-N-D-E-R-S. Brilliant Blunders. This is by Mario something. Mario Livio. And this is a book which tells that how great physicists have made great blunders, but still these blunders to be great. And here it is a mention of cosmological constant, that Einstein thought that the universe is constant, but later through Hubble telescope, we found that it is accelerating. Okay. 8 pi g, this is actually coming from what is called Poisson's equation. I will later explain it. It is, again, I have to go into a lot of other things. So we know, and c to the power 4, actually already Francisco has explained, it is a kind of a dimensional analysis when through equation, if you see the derivation comes up to that. Interesting part is one friend which is still standing alone and is telling Francisco and me, why don't you talk about me? That is called the T mu nu. And this is the stress energy momentum tensor. We know what is stress, Newtonian mechanics. We know what is shear stress and strain. But here you see, again, this is framed in a tensor which contains 4 dimensions of space-time. Now, what actually a stress energy momentum tensor does, for example, it is a box. Let us imagine to be a box. So anything related to stress, strain, dust particles, or anything which relates to the formation of matter, not the subatomic realm, let us understand, but on a macrocosm realm, macrocosmic realm, whatever relates to this energy, mass, momentum, we are talking about momentum, right? So everything has been framed in this single object, that is T mu nu, which is called a stress energy momentum tensor. I will come up, if you want, in a separate video in a podcast where I can explain each and every component of stress energy momentum tensor. This is energy density, this is pressure. It contains a 16 matrix. It's a 4x4 matrix. So it has got a lot of stuffs like that. So that is stress energy momentum tensor. So what we understood finally from this discussion is that the left-hand side speaks of the curvature, how much curvature has taken place. And the right-hand side actually speaks of the stress energy momentum tensor. That means how much, obviously, if there is no energy density or there is nothing which is called, denser, then how it will cause a curvature. But here you see, Francisco, we have omitted a very significant and a subtle thing. What is that? If we go back to special theory of relativity and Einstein's most famous equation, it says E equals to mc squared. If I omit the c squared part, and if I take this part, then it will say energy is equal to mass, and mass is equal to energy. Now you see in this equation, I would also like to make the viewers notice exactly that is here. You see this T, this is energy. This is stress energy momentum tensor. That means stress is there, energy is there, and momentum is also there. Now remember, this stress energy tensor was also there in Maxwell's equation, also there in Newton's equation, but that was in a vector form. That was called stress energy vector. And we have done a lot of mathematics in our school days on stress energy vectors. Now you see here, that is the problem, Francisco, that vector cannot define only the, what can vectors define? Magnitude and direction. Now, if I get a 3-dimensional plane, I don't have a 3-dimensional box, then other than the magnitude and direction, you might ask, okay, Shounak, tell me on which plane this force is happening. You can visualize a box. And then on the backhand side, I need to know which plane it is, the back, the forth, the inside, the outside, right? So that is what is tensor doing. Tensor is something which not only tells the direction, the magnitude, not only the direction, but also on which plane it is happening, and that which vector cannot do. That is why we need tensors. Now, coming back, what I was telling, that if energy is equal to mass and mass is equal to energy, and we know that mass causes space-time curvature, we get the answer right over here. So T is the stress energy momentum tensor. That means it has got stress and energy. And what is this energy causing? Energy is equals to mass. And you see the left-hand side equation, it talks exactly that mass is causing the arm moving and all those curvature. So you see how beautifully we have today derived that from the simple equation of E equal to M, I'm omitting C square, E equal to M, that same thing is now being generalized into Einstein field equation. Energy is on the right-hand side. That is the stress energy momentum tensor. And mass is on the left-hand side. That is the curvature because of the presence. Isn't that a beautiful theory?
So fascinating, so fascinating. I do believe, I do understand why many people, but have been, like for example, the last guest I had was Udipta. We talked about gravitational waves, and so also about a little bit about general relativity very briefly, and he said that, and I also asked him what was his favorite theory, and he said that general relativity. And I do understand why many people do think this about general relativity, because it is just extremely fascinating.
Beautiful. It's beautiful. And one more thing, sorry to interfere. I don't have the slides over now. This equation is so beautiful as a flower, as beautiful as a red rose. You know why it is beautiful? Now, when do we call a thing to be beautiful? When we can relate things. Now, this equation, I will say you the left-hand side and the right-hand side, right? This equation is exactly the same which Isaac Newton told in his Principia Mathematica. How? The F equals to G m1 m2 by r squared, which calls the famous equation of gravitation. That equation is the left-hand side. So the gravity equation, which we call gravity, we started right as a fictitious force, that F equals to G m1 m2 whole divided by r squared is exactly generalized by the left-hand side. That is, gravity is a space-time curvature. Hold on. There is another beautiful thing, a beautiful violet, and that is the right-hand side. We know by the second order differential equation, we can deduce F equals to ma. Force equals to mass time acceleration. And this mass time acceleration actually causes what Francisco just questioned me beautifully. What is a geodesic? Now, that acceleration, that means that movement is no more a movement. That movement has now turned into a geodesic form, and that geodesic is responsible for causing the mass of the space-time curvature, which is the right-hand side. The geodesic equation is quite huge. I mean to say, even I say, oh my goodness, don't show me that. It is fearful. It's extremely complicated. But I can summarize this, that the left-hand side of Einstein's field equation is the famous gravitational equation of Newton, F equals to G m1 m2 by r squared, and the monstrous geodesic equation is nothing but F equals to ma. And that is called the beauty of mathematics. That is called the beauty of science. And remember, we might be speaking about exact solutions of Einstein field equation, when we will see that under extremely low conditions, that means not very big mass, not spherically round, I mean to say absolutely spherically now, no, I would say energy, no much of electricity, etc. These equations of Newton would go back to, I would say Einstein's, would go back to Newton's equation. And if you've taken a spherical ball of mass, which is kind of a Schwarzschild radius, and it doesn't have a movement, it is all symmetric, then from Newton's equation, you can come back to Einstein's field equations. So nothing is violated, Francisco. In nature, we say everything balances. You now see Newton's law, which I, a few days back, made a video called No Scientific Theory is Wrong. So we cannot tell Newton is wrong. Come on, that is idiotic. So Newton's laws of equations, under certain conditions, very simple conditions, can be regenerated to Einstein's field equations. And Einstein's field equation under symmetrical conditions can go back to Newton's law. So everything remains, the symmetry remains, everything is as it is, and we are happy, you are happy that we can understand partly Einstein's field equations.
It's very, very, very fascinating, I do believe, I do find it. But you mentioned, you just mentioned now Schwarzschild, a Schwarzschild radius, and I want to pick up on that and let's say start introducing the last question that I will ask you for the episode of today. And I want to introduce Karl Schwarzschild, which was physicist, I believe. He was a physicist.
Astrophysicist. He was basically an astrophysicist at Göttingen University, as well as a mathematician and physicist. Right.
Okay. And he basically, after Einstein field equation got published, he started, let's say, playing with it, and he managed to solve. He managed to get one of the first solution of Einstein field equation. So he derived a solution of this equation, and I would like to show it here mathematically. Now I believe Schwarz. I think I will not write the name correctly, but hopefully Google will understand.
SCHWARZ. SCHWARZ. Yeah. Schwarzschild radius. Yeah, you got it. Yep.
Yes. So
you can click on the third one. That is better. RS is equal to 2gm by c squared, right? Yeah. Yeah. This one.
Yep.
R equals to 2gm. Okay.
Okay. So basically, what happens that this guy said brutally. This guy manages to solve Einstein field equation for a solution, and this solution basically is quite mind-boggling for people at the time because it says that if you have a mass which shrinks down through a critical radius, which is indeed what you said, a Schwarzschild radius, if this happens, then that mass, that object, will start collapsing into a black hole, which is a place where space-time curvature is infinite, density is infinite, no light can escape that. And that's, let's say, makes sense why many people at the time, Einstein included, believed that none of these objects could exist in the universe. Now we know they do exist, and we know they have, let's say, they have a point at the very center of a black hole. At the very center of this object, there is a point which is called the black hole singularity, which is the point where where density and space-time curvature are infinite. Literally, we do see appearing an infinite in Einstein field equation. And now I ask you, why do we, let's say, why does it break down general relativity in a black hole singularity? Why are points that really challenges our understanding of the laws of physics as we know them?
Sure. Before that, I would like to tell the viewers a fascinating yet a motivational story about this gentleman, Schwarzschild. Now, I remember possibly the date was around 24th of December, just before Christmas in 1915, when Germany was in First World War. Now, you understand that during that time when Germany was in war, the First Reich was actually taking all those people who can fight the war. But remember, Schwarzschild was 41 years. Anybody more than 40 cannot join an army. But because he was great in calculation of ballistic missiles or ballistic equations of the motion of objects going, so he was asked to join, and he was just doing the calculations under the trench. See how motivational it is. I hope Francisco will also appreciate that. Now, on 24th of December, 1915, Albert Einstein received a letter, and that whole envelope was full of dust and mud, and there were certain blood stains. And he opened the envelope, and he found that it was Karl Schwarzschild who has found out the first exact solution of Einstein's field equations working and staying under the bunker of First World War. Remember, today we require MATLAB and many other mathematical applications to solve Einstein's equations, but just with a piece of pen and a paper, staying under the bunker when the World War was on full-fledged, was waged, This gentleman can solve the hardest and the most difficult problem. And today we tell our children that you need an AC room, you need a nice place, you need a table and a chair differently in order to do maths of class 10, 11 or BSc. But that is not the case. Let us remember, if you really want to do, you can do from the trenches of First World War. Anyway, so that was really motivating for me. Now, what Schwarzschild found was that a critical radius, which is the Schwarzschild radius, that means given this this glass, if I can squeeze, given this object, if I can squeeze further beyond this R, that is 2 gm by c squared, then it will turn into a black hole. Okay. Now, this was the first solution. Solution means that if I put these values, something concrete will come out. Just we have solutions and no solutions and two solutions for differential equations. Now, the problem was that Schwarzschild assumed certain very favorable conditions. Now, as you understand, it is very difficult to solve partial differential or Einstein's equation, given lot of curvature, lot of gravity, lot of acceleration, lot of movement, lot of particles. So he assumed let A equals to 0, let B equals to 0, let C equal to 1, and let D equal to 0. In this way, he assumed something. These are called conditions of Einstein field equations. And the more you assume conditions, the less perfect it becomes, because you're assuming a lot of things, right? Which is not that, because a black hole won't be a static black hole. It would rotate. A black hole won't be non-chargeable. It would have a charge. But anyway, that was a historical part. So he, assuming those things, find out what is called a Schwarzschild radius. Now, as you see, this was what you really asked, that Carl Schwarzschild first found out that if this application is done for a particular object, it becomes a black hole. Now, see, black hole itself is a problem, and I consider this still to be a problem, because mathematicians and physicists do not like undefined terms or infinity. Even in quantum mechanics, we try to avoid infinity, and we normalize the equation and we get into value either 0 or 1, right? Now, there is one misconception. Is it undefined at singularity or is it infinity? Question is that 1 upon 0 is undefined, not infinity. I would like to make a close note of that. See, if we get an infinity, it is not a problem. Since age-old Greek times, I think Aristotle, Socrates, during that time, we have been calculating infinity, either philosophically or mathematically, not a problem. But infinity is not the problem, my dear. The problem is the undefined. So at the singularity, what means that laws of physics breaks down? That means we get something which is undefined. Singularity is nothing very recent to Einstein relativity. Again, a wrong. No, it was there in mathematics many years back. It is there in topology, which Gregory Perelman solved through Ricci surgery, which Richard Hamilton got stuck up. So a singularity is nothing new. The problem is that we get an undefined term. I can show you, I don't have right now. If we show the entire Schwarzschild equation applied to a black hole, you will see it comes something like 1 upon 0 or something like that. And it will actually blow up to infinity. Yeah. No, this is the metric which is showing. Yeah, you can click on that. Let me see. Yeah. Okay, so you see here, that's great. Okay, don't change it. You see, yeah, this is beautiful. Now see, 1 minus RS by R. Okay, I will now make a point. Forget everything. dr squared, these are polar coordinates, spherical coordinates, for example. Just note this one. ds square is the invariant line element, fine, but minus, then within braces, 1 upon RS by R. What is RS? That is the Schwarzschild radius, right? Now, if we take that as unit 1, right? We put 1 minus 1. I take RS as 1. Now, this R is basically the radius from the center of the black hole till the event horizon. Okay? Now, a body approaching. What will happen? It will shrink due to time dilation, and this denominator R will become 0. I mean to say the radius, when the body touches to black hole or approaches the singularity, it will reduce to 0. So what will then happen? 1 minus 1 or RS upon 0. This will become undefined terms.
Wait, Shounak, I don't understand. Why do we have a radius R that becomes
that is R
0?
right from the center, yeah, from the center of the black hole till the event horizon. That is the center, or a spherical mass, anything. The body approaching, what will happen? The R reduces further, and it hits the singularity.
So basically when it is, when if I understand correctly, when the event horizon shrinks.
No, not the event horizon. The body has crossed the event horizon. Now I am approaching to singularity. The radius is further shrinking and shrinking and shrinking and shrinking, and it touches the infinity, the singularity. So the radius mathematically from 5, 4, 3, 2, 1 will reduce to 0.
Okay.
Now, if
so
it reduces to
we have
0,
we have an object with the radius that is basically no radius.
Yeah, absolutely.
Okay.
Absolutely. So it reduces and it goes to 0. So anything 1 upon 0, it becomes undefined, not infinity. Again, I'm saying infinity is not a problem. We can deal with infinity with limits, etc. And same happens with this one, radial contraction of length. So it is, as I told you, it is radially contracting. You see, it is already written. I'm sorry, I didn't see that part. Radially contracting the length. Contracting further, and then the R becomes 0. So that is the problem. Now, you might ask me what happens? The answer is we don't know. Because these, again, are very hypothetical and extreme objects. But mathematically, we say that we don't have an answer. Mathematically, again, I'm stressing this term, mathematically, we say that it blows up to infinity or undefined. Now, this is actually the problem with Hawking radiation also. Quantum mechanics, on the other hand, we do have the methods, mathematics, and equipments to measure quantum entanglement, superposition, etc. But these conditions are so extreme, forget about reaching black hole. I mean to say, maybe crores miles apart, we really don't know. So that is the problem with theoretical physics and applied science. This is so theoretical that we can only guess, understand, deduce the theoretical solutions and get to that. So that is how it stands out to be.
Okay. So basically, when there are some people talking about the fact that we do have infinite time dilation when we reach
time dilation is infinite. See, when we do the mathematics, time dilation might be infinite. See, I mean to say it is very simple. So there is a rubber band, and the rubber band is, or a spring is up to this size. So from here to here, it's just 1 second for the time to reach. And we stretch and stretch and stretch and stretch further. And the spring becomes this long. So obviously the time taken will be more. And why this length increases, or why it is so? Because of the gravitational curvature. Because the gravitational curvature is so extreme at the black hole that the light wavelength stretches so much to infinity that if I am falling in the black hole, say for example, I should not, because I have a lot of work to do. Say for example, if I am falling inside the black hole and Francisco is measuring that from a certain point, Francisco will always find me never reaching at that point. That is infinity, because it stretches, and light will always show that me, Shounak, is somewhere near the event horizon. But the fact is that I have always reached the singularity and I am dead, or I'm stretched to infinity. So as there is a common notion that does time stop near a black hole? No, my dear. Time doesn't stop near a black hole. In my watch, time will be running exactly the same. Only you will see that I am never reached, or I'm still hovering around the event horizon, because light is taking infinite time to reach your cornea or eyes. And why it is taking time? Because the gravitational curvature is so much that the length of the wavelength of the line stretches and stretches and stretches.
Okay, so basically when people say that we have infinite time dilation, and now I'm talking about the equation here, it's because when we have 1 minus, let's say 1 as a child radius, 1 minus, but in this case, if people say there is infinite time dilation, it means that here, this term gets 1 minus 1 over 0. So we have, in this case,
but there is a problem.
1 over
no,
0?
In this case, no. What we are saying is different. See, this is a Schwarzschild solution. That means this is applicable at the event at the singularity where already we are getting those terms undefined. But if we take time dilation, taking the Lorentz factor, root over 1 minus v square by c square, and if the v square reaches up to infinity or it turns up to 1 upon 0 or something like that, then we get a time dilation which is observable by generalized. There is a difference. The frame of reference that you are talking about, that time dilation is observable. That is observable universe, or mathematically we get up to infinity. But this is not observable. That means there is no question of time dilation at all. This is definitely mathematically a time dilation, but we won't be able to see that because we will never be able to reach that position where this entire equation blows up to undefined. You got my point. One frame of reference where we can watch those things. And, time dilation, length contraction, these are observable if we are moving at the speed of light. Or even gravitational time, I would say gravitational lensing. You see that this Hubble, this new, what is the name, that new space telescope after Hubble? What is that name? James Webb. Yeah. So James Webb is now picking up multiple images of the same galaxy. Why it is happening? Because it is showing the same image, the front and the back, because of the time dilation factor. Because light is curving from the back, so we can see the back of our head. We cannot see it right now, but if we do that, the time dilation, that is the gravitational lensing factor that is in the observable universe. But this is to extreme conditions where everything is undefined. Mathematically, yes, this is a time dilation, but it is not observable. Obviously, time will be dilated because if it is going to something to undefined terms, then I mean to say, where do we stand? We don't see light. I mean to say, we don't see anything. And obviously the radial length contraction, because this is a what we call spherical coordinates. So if you approach in this way, it actually contracts like this. So it is a radial length contraction. But question is that which is the frame of reference that we are referring? That we sometimes forget. Now, length contraction in special relativity or time dilation, when does it happen? Now you tell me. When we are accelerating a body at the speed of light. Now, have you, me, our parents, father, mother, your friend, have we ever moved at the speed of light? No. That is the question, very common sense, that if we do not move at the speed of light, these are all mathematical calculations. These are on mathematics, but we have never accelerated an elephant or a ball at the speed of light and have seen. Yes, now we are doing at the particle accelerator, at LIGO, etc. Anyway, I think I'm going hayward. Please, sorry for that. There's a lot of other things are being discussed.
Absolutely. No, there is surely a lot to do, but I think that actually, fortunately, we will meet again. So sure. I can stop sharing the screen. I think we have enough.
Let me summarize before we close down, because it will be easier for the viewers to understand. So in this episode, what we did is that we understood a little bit of history of general relativity, how it evolved, and we learned about what made Einstein found out that gravity doesn't exist. Then we further found out what are the different components of Einstein's field equations, how these components are, I would say, how these components are related to measuring the space-time curvature. We cannot use Einstein's field equation in order to measure curvature of normal terrestrial things. And we went a little bit in Schwarzschild radius, and we find out that gravitational time dilation is something which causes the light to reach to a point of infinity. And that is why we can see always the object hovering around event horizon, but never reaching inside and annihilating. And we learned a little bit about Schwarzschild radius. So from my side, it was a very insightful discussion. I think we talked about an hour, but it exceeded, but I think it is great. So thanks, Francisco, for getting me here.
Yeah,
and,
absolutely. It is my pleasure. So yeah, that was the summary, but we are not done yet, because we will come back again with some other, let's say, question that we will lead our conversation. So stay tuned, everyone. And of course, I want to thank Shounak for your kind availability, for your time and your great explanation. You are
always a pleasure to serve to science and mathematics. And I'm sure that Francisco is doing a job. I request all the viewers to share as much as you can about Francisco's videos, his works, because you see, this is something, a real noble work that we are doing. That I mean to say, what he is doing is a noble work to the society. It is not always that you do something and you get paid for that. It is not that, because it's just sheer love of, yeah, it is just sheer love of mathematics and science that Francisco has been serving. And there are a lot of good people who have come. I didn't get the time to watch, but surely that it is a noble job. And from my core of my heart, I thanks and wish him all the best to carry on this journey into science and mathematics.
Thank you very much, Shounak. We will meet again very soon. So everyone, stay tuned. We will come back in this channel, in this podcast. We will keep on going with some other questions relating general relativity, but we also want to cover and span other topics. So it is very exciting. The future is very exciting, and I am thrilled to tackle it with Shounak. So thank you again, Shounak, for your time. And thanks everyone for being with us today. And I hope you had fun. I will see you in the next episode. Bye.
Thank you very much. Bye.